First, thank you. Thanks for the organizers for putting on what I think is an awesome conference. Thanks for the volunteers, sponsors who make it possible. The transcriptionist is doing an awesome job. Thanks to University of Washington, whose beautiful hall we are standing. And I also would like to acknowledge that the land we're standing on is the traditional land of the Duwamish people and of their neighboring tribes of the Puget Sound. And you may have seen some of their art around town. I see a lot of it. The topic of my talk is about being a student of all the things. And you, one second. There we go. And you may know this cartoon from Hyperbole and a Half, all the things. And it speaks to me because I think I've always been some sort of student and sometimes an instructor. And many of us are also students of Python on their own, not necessarily in a formal setting, in a software engineering or computer science setting. And I am as I said, I'm an earth scientist. Earth scientists write programs. I shuffle around a lot of data. I do visualizations, make maps, and sometimes I do some machine learning. And I sometimes teach programming. I had the opportunity to teach programming to undergraduate and graduate earth scientists and mentor students with their programming, often in Python and often open source or other non-open source languages. And it's a little secret that scientists or students, and I'm just kind of use it really broadly, you know, pretty much everybody should somehow fit under student somewhere, often write kind of quite mediocre or bad code. And that's really well known if you just go out on an internet search engine of your choice and look for examples, and there are many examples where people talk about how scientists' coding is really not up to par. There are big problems in looking at the code oneself. Often the code is not available. If it's there, it's not documented. If it's documented, weird approaches to testing. This is Alice Harpole writing for the Software Sustainability Institute. It's difficult to work out how it works, how it runs, and that's kind of not really good for science, right? We want to be reproducible. We want to do something that others can check, and it's code, and there's data, and it should be easy to run. This is a writer, Bojidar, I think, maybe I'm pronouncing it wrong, and he seems to be having a pretty often quoted article about this exact problem, and he just rips into it. Can't write good code, they write code simply, and this is actually really interesting. He makes a good analysis. They write code, we write code simply to achieve our immediate goal. We get it to work, it works, and then we hand in a paper for our professor or write a paper or we're done. Or like the data is now where it should be. And so we throw it away afterwards. Bojidar here quotes all sorts of software engineering things, API design, code coverage, code quality, and he says these things are rarely done properly in the scientific community, and he's right. Then here's a guy called Neil Saunders. He's a data scientist, and he quite openly admits, yeah, it gets ugly, and he says basically what we're doing is we are writing our exploratory data analysis, and then we're done, and we're never getting around to actually cleaning it up. So people, of course, are constructive, kind of. They propose some remedies. For example, teach scientists code organization, all the stuff that software engineers know, or hire software programmers into the research institutions. And some are kind of bold and say, it's all good. We need to make a mess, and it doesn't matter if it's bad. Well, I don't actually believe that. I think it does matter. And I also think that all of these things, other than the third, are good, are important, and are right. But they're not all of it. What about the actual code? You know, even if I teach all the software engineering practices and version control and organization, people don't magically become better coders. And what I'm trying to convey today is that we can and should also work either ourselves or with people we mentor. And I was really lucky. I had excellent mentors with Python and still have excellent mentors. That that we should really work on writing better code. And the second proposition is that we, looking through the lens of abstraction and thinking a little deeper what is meant by the term abstraction can help. And this is how. Abstraction, the way I understand it here, is actually starting like at the basement level, not like up here at object-oriented design, some book with a very abstract book, like we're staying like down here. Just abstraction. Abstract is the opposite of concrete. Abstract is about how I conceptualize something, what the mental chunks are that I use to think about something. And if you look at the Python documentation and look for the term abstraction, there are a few really good places where it comes out, and one you've already seen in the second talk by Al Schweigert, exactly the same passage that he quoted, section 3.1, object values and types. He was interested in the values. I'm interested in the first line here. Objects are Python's abstraction for data. We know in Python everything is an object, and there is data, and an abstraction is what how the object represents the data. And there is, at the end of this paragraph, also a little thing. It's not just everything is data in our model, so even code is data, so it's not just about data, scientifically speaking, but also code. Then in several module documentations, we find something about abstraction. Here, this is the URL-lib documentation. It says this class, the URL-lib.request.request class, is an abstraction of a URL request, meaning we get a class from this module, and it represents, it's an abstraction for a URL request, which in some ways is more concrete. It's something that actually happens on some level in the real world. This is from the SSL module documentation, and here it talks a little bit about how SSL sockets are an abstraction, and also similarly OS level sockets. So the socket idea in this module is an abstraction for something that happens. There is also a little warning that you can find in the programming FAQ, and I will just put this here and come to it later. It says a little bit, it says in the performance section that if you create abstractions, it has a performance cost, and it has this idea of excessive abstraction. So it's a hierarchical thing, or at least it's a level thing, a layer cake of abstractions that are building on top of each other. And this FAQ says, well, be careful, don't abstract too much, whatever that means, and we'll come to it. Yeah, note the levels. Now, if I say abstractions, is this something that students or beginners in Python will take years to get to? Well, no, not at all. You deal with abstractions right away. And I'm giving an example, and, well, I will talk about it. Like, let's say I'm still having my scientific student in mind who, for example, might want to open a data file, and someone gave them the data file in JSON format. So you would just read the content of the file into a variable called data, which might be, well, I hear is another option is like you have it in a string, so you use JSON.loadString. And here's an example of like a data set, and there's maybe some sort of measurement. There's a species, Betula, that's a birch tree, and a date stamp when it happened, and a temperature, whatever, you know, just some dummy data. So I'll come back to this. If they do this, and you look at the data dictionary the output will be a dictionary. You look at the dictionary and look at the value data set of temp, you get 28.4. Data set of date stamp, you get what's written there. I tried it, really. So this date stamp, what is that, abstraction-wise? Like, what is the nature of it? What is the type of it? It's a string. It's not a date stamp. It's not a date type thing. It's a string thing. And I cannot tell you how many times I saw people that I meet in academia stumble exactly here. They read some data in. You see the temperature comes out as a floating point or something, okay? In this case, we are kind of in the right category. It's a number, it stays a number. But this comes out as a string. And then they want to do something with the string. They want to reformat it, and they think about it as a string. So they start to substring it and slice it, and then they convert it from string to integer, and then they add something, and then they have to put it back together, and then they remember there's a datetime module halfway through, and instead of taking 2 lines to convert this here with strip time and struff time, they take ages and they have very error-prone, non-readable, non-portable code. Because they stuck there at having a string instead of saying, what I actually need is a datetime object and not a string. It's really simple. And I've had many students go, ooh, really? That's how I should think about it. You would think, I'm sure that pretty much all of you or many of you will have passed over this point, but if you mentor someone, stay there and give it a moment. So this was just a basic example. How else do we encounter this in Python when we work with it, when we learn it? Well, duck typing is about abstraction and abstraction levels. Again, from the Python language referent, an object's type determines the operations that the object supports. And if you teach someone or work with another language that is not Python, it's another interpreted language, often enough you don't come to this point where you think about the operation that something supports. You just have lists or arrays or whatever that go one way and then some other data type that goes another way. Whereas in Python it's really important to think about that. And usually it goes in 3 steps. For example, with the most basic thing, a for loop through a list. You have many beginners who write this. They've had a programming class. They learned that you have to get through a list sort of thing or array sort of thing, you have to have an index and you increment the index. And that means that they think about this list in a certain way. They think about this list as something that has an index and that I have to increment to get through it. And I'm sure under the hood that is absolutely true even for Python, for C Python. I'm not sure, I'm just guessing here, but we're writing Python and not C. And that means that the student is not wrong. It's just the wrong abstraction level for Python. So we teach them, this is how you should do it, 4 element in my list. And when we teach them that, we also switch how they think about lists in this case. They think now about list as something that has elements, and that elements can be accessed sequentially, and you get the sequence automatically. You don't have to worry about it. You don't have to define an index. What I didn't give you here was that, of course, sometimes we want an index, and then we can use enumerate, right? So we don't use the first version at all anymore. But this is only step 2. And then step 3 is the one where duck typing comes in. Now we teach them it's not just lists. The exact same code for element in my iterable works for any iterable. And then this is really not to the big gotcha. It's really something that I think Python is really good about because Python is so consistent about these things. It's very much designed with attention to detail in these areas. In MATLAB, you have also a for element equals something thing, but it's element equals my vector. Students get really confused about that. Anyhow, another example, just briefly to mention it, is file-like objects. You can turn all sorts of things into file-like objects with, for example, the I/O module, and also sockets or serial interfaces. If you do CircuitPython, you want to have serial interfaces. You can read from the serial port, work just like that. So you turn everything into something that you access by opening it, by reading from it, maybe writing to it, and closing it, which is like a file. So at one point, you get to the point of getting to write your own abstractions. And that happens, for example, the first time when you write a function. Because a function is about how to segment a processing flow, like I'm thinking again mostly about the prototypical sciencey student. There is some processing to be done, into steps and functions. And then if you write bigger things, modules, packages, maybe you release something. But this is also a question about what are my mental chunks. It's an expression of how you conceptualize your task. And what this gets you is reusing, passing around data, and also hiding your implementation choice inside your functions. and you access just the API that you just created yourself. I call this abstraction for problem solving. Then data representation. It's very similar, but slightly different, because you think sometimes about what comes first. Is the main thing I'm talking about the data, or is the main thing the operations I do? If we heard about these neural networks and other model building and machine learning, often enough you think of your functions first. In this case, the data is already standardized in some sort of API that you get from pandas or NumPy or something like that. But then you think about your conceptualizing of your model building, validation, etc. You develop the abstractions for your data and the abstractions for your processing steps hand in hand, and they have to fit each other. With a library, you get certain things for free, and then you bolt on that. Also, the data representation in the end decides what your objects are, whether you work with a table-like thing, which I don't, or with a pandas data frame, which is a thing you get used to. You get used to certain properties that it had, or a NumPy array, or if you stay within the standard library, a list, a set, a dictionary, you get used to thinking about the objects in what they are. I call this like reasoning about the overall shape of your problem or problem domain that you're working on. And tying it together, the transition to the object-oriented design sense of abstraction, where you then work about encapsulation and things I've really only personally don't feel like an expert about at all, it becomes quite natural. What's kind of sad is that I know a lot of scientific Python users, even quite well-versed ones, would never ever write their own objects. They just write procedural code and everything. They write functions, but if you think about it like this, you get actually quite naturally to writing objects. At least that's my experience with my students. And we can talk quickly about, we have a transition to what the computer science and software engineering people learn in their object-oriented books. Last, and to just kind of come to the little, and I'm not saying, rah, go ahead and abstract everything, abstract all the things. There are some pitfalls here that you need to be careful about. The notion of leaky abstractions, I forgot who actually created or invented the idea. The idea is it's leaky like a sieve, you know, there's water coming through. You can look through one level of abstraction through the underlying level, and Python is actually kind of quite leaky. We saw the talk about debugging showed us some error messages and how error messages or exceptions sometimes don't actually tell you where the problem occurred because it's hidden within successive function calls. Sometimes you really don't know, like if you forget, if you do mistakes, if you make mistakes where you use brackets instead of parentheses or vice versa, you get very strange error messages that have nothing to do with what your actual problem is. Sometimes just these messages are on the wrong abstraction level. I believe there has been some work lately done, I believe in Python 3. What's currently being worked on, where some of the error messages look a lot improved, so that goes in the direction of making things more consistent. Also, objects, you can always use dunder-dict, right, to turn an object into, like look into an object in the form of a dictionary and forget about what the object is supposed to represent and stop reasoning about the object as the object it is, or the class it is, but look at it under the hood as a dictionary. Yeah, that happens, but you can deal with it. It's quite pragmatic sort of thing. Also, I did not want to go into details here for time reasons, but some of the Python gotchas have, I think, to do with how abstractions work. The famous mutable default function argument gotcha, if you have encountered it, you know what I mean. If not, look it up. It means basically if you have a function and the function has arguments and you set default arguments with argument equals something and the something is a mutable object, you may not get what you expect because it is not limited to the scope of the function and gets reinitialized every time. You sort of get yourself a hidden thing that almost works like a global object, and it's probably the only gotcha I've personally encountered in the wild, like my own code failed because of it. So you think of it, why does it have to do with abstraction? It has to do with abstraction because you think of a default argument as something that's inside the function and doesn't have a life outside the function. It does, unfortunately. So, and then the performance warning that we got in the quote I had from the Python FAQ. Abstraction, simplicity, performance shows two, basically. If you really want to design your abstractions so that they fit your real-world problem 100%, you will probably get a performance hit. I saw, there are some great people to follow on Twitter. I saw, my mind gets blank, I forgot who it was, who just said, well, there is a dunder slots thing you can use to improve performance. So yeah, so there are ways around this though in Python, and specifically if you use Python for science, you get actually a lot of optimized things within NumPy. You get extensions to it that make performance faster, so Python isn't even so slow anymore. But be aware of it. It's not the solution to all problems, and sometimes you want to have a simpler thing that is a less elaborate abstraction level. Yep, so thank you. This is what I wanted to tell you, and I hope you had fun with it.